Okay, in order to solve this problem, we need to set up two equations in the standard form, plugging in our xy values from the two given points. So first we'll get 4 is equal to a times 2 squared plus b times 2 plus c, which gives us the equation 4 is equal to 4a plus 2b plus c. Similarly, we'll get 2 is equal to a times 4 squared plus b times 4 plus c, which gives us the equation 2 is equal to 16a plus 4b plus c. Now we'll subtract one of these equations from the other. The c's will automatically disappear, and that's going to allow us to get a and b in terms of each other. So when we do that, we're going to get that we'll subtract the first equation from the second to get negative 2 is equal to 12a plus 2b, which means that negative 1 is equal to 6a plus b, which means that b is equal to negative 6a plus 1. Now we'll go back and substitute in for b in this equation, and we'll now have 4 is equal to 4a plus 2 times b, which we now will replace with negative 6a minus 1. There should be a minus 1 here. So here we have the, here we have negative 1 equals 6a plus b, so b equals negative 6a minus 1, so this is minus 1 here, and then that's plus c. So we've replaced b with negative 6a minus 1. Okay, that's going to give us that 4 is equal to 4a minus 12a minus 2 plus c. We'll move everything but the c over to the other side to get 6 is equal to, and 4a minus 12a combine to negative 8a, so we'll get 4 equals negative 8a plus c, or rather 6 equals negative 8a plus c, which gives us that 6 plus 8a is equal to c. So now we can replace b and c, and we get ax squared plus, instead of b, we'll get negative 6a minus 1 times x plus our c value, or 8a plus 6. Now if I plug in any value for a, I'll get a parabola that passes through our two given points here. Okay, what is the value of k such that the equation x squared plus 4x plus 6 equals 3x squared minus 2x plus k has exactly one solution? Okay, in order to do this, we want to set this up to be a quadratic with a set equal to a value of 0, which means we can then use the quadratic formula, and whenever we see a question about number of solutions, we know we're dealing with the discriminant of b squared minus 4ac. All right, so first thing we'll do is we will subtract x squared plus 4x plus 6 from both sides to get that 0 is equal to 2x squared. We subtract 4x from both sides to get negative 6x. We subtract 6 from both sides to get plus k minus 6. And we know that in order for this to have exactly one solution, the discriminant, b squared minus 4ac, must have a value equal to 0. So when we plug in, we're going to get that negative b squared, or negative 6 squared, minus 4 times our a value of 2 times our c value of k minus 6. We know that this has to equal 0. That's going to give us 36 minus 8 times k minus 6 is equal to 0, or 36 minus 8k plus 48 is equal to 0, which is going to give us that, that's going to give us that, therefore, when we add these together, we get 84 minus 8k is equal to 0, or 84 is equal to 8k. K is equal to 10.5. So if we replace k with 10 squared, this equation here will have exactly one solution. Okay, 5 key points of this parabola here. Let's first find the vertex, which is going to have an x value of negative b over 2a, which gives us negative of negative 5 over 2 times 1, which is equal to 5 halves, or 2.5. We substitute that in to get our y value for the vertex, so we get 2.5 squared, x squared, minus 5 times 2.5 minus 14 is going to give us 6.25, minus 12.5 minus 14 is going to give us negative 20.25. So that gives us our vertex at 2.5, comma, 20.25. Negative 20.25, that is. Negative 20.25. And that means that we can now move on to figure out our next point. So negative 20.25. Okay, our y-intercept is clearly going to be 0, negative 14. The x value of the reflection of our y-intercept is going to be equal to double the x value of the vertex. And the reason is that we have to move from 0 over to x equals 2.5 because that's where our line of symmetry is. And then we move another 2.5 to get to the reflection of this point, which means that we're going to have 5, negative 14 as the y-intercept reflection. Okay, last thing, we want to find the roots, and we can either use quadratic formula or, if appropriate, we can factor. In this case, if we quickly check b squared minus 4ac, we get 25 minus 1, 4 times 1 times negative 14, which gives us 25 plus 56, which gives us 81. And when b squared minus 4ac is a perfect square, as it is in this case, then we know that our quadratic is factorable. In this case, the factorization would give us x minus 7 times x plus 2, which means that our roots are going to be at x is equal to 7. And so we get 7, 0 as one of our roots, and we get negative 2, 0 as our other roots. So there we have our 5 key points. We have our vertex, we have our y-intercept, we have the reflection of our y-intercept, and we have our 2 x-intercepts. Those are our 5 key points. Problem here. Okay, so let's take a look at our next. Okay, number 4 can't really work through here without the graphing calculator, but you will end up here with the points. A vertex is equal to negative 5.68 and y value of negative 7.42. Your roots are going to be at negative 18.67 and a positive 7.3. Your y-intercept is going to be at 0, negative 6, which means that your reflection of that will be at the point negative 11.36, negative 6. Notice a couple things here, that this x value of negative 5.68 is halfway between our 2 roots, which are the x values of our x-intercepts. Also halfway between 0 and negative 11.36, which are the 2 x values of our y-intercept and our reflection of our y-intercept. And that's again because for any parabola, we have right through the vertex a line of symmetry, and any point on either side, although it doesn't look like that from my drawing, these 2 points will be equidistant from the x value of this vertex here. Okay, let's take a look at this next problem. All right, so here we have now this action figure which cost $6. We sold 100,000 units last year, and according to our market research, every 10-cent decrease in price will lead to 5,000 more units sold. All right, so let's say our revenues then will be equal to our price, and our price is going to be our starting price minus 0.1 times the number of price decreases. In other words, for every time we decrease by 0.1 or 10 cents, that changes our price. And what it also does is change the number of units that we'll sell, and for every decrease of 10 cents in price, we're going to add 5,000 more in units sold. Okay, so X in this case represents the number of decreases, each decrease being 10 cents in value. All right, to maximize our revenues, we want to find the vertex of this quadratic. We can quickly tell that the zero values for this are going to be when X is equal to 60, which means that we reduce the price by 10 cents 60 times all the way down to 0, which means that no matter how many we sell, we're only going to have 0 revenues. On the other hand, when X is equal to, from here, negative 20, it means that we have raised our price to a point where no one wants to buy this thing anymore, and so our revenues are 0. In between 60 and negative 20, we end up with the value of 20, halfway between these two, which means that our optimal decrease in price will be 6 minus 0.1 times 20, which means, in other words, we reduced our price by 20 chunks of 10 cents apiece, or this is going to turn out to be $4. Then what that does to our sales is we increase our sales by 5,000 times 20. And so our new revenues will be $4, 6 minus 0.1 times 20, multiplied by 100,000 plus 20 times 5,000, or 200,000. And that gives us 800,000 in revenues, and that will be our maximum. Okay. Now for our next, we're saying, all right, the company decides it wants to set the price as low as possible while still earning 700,000 or more in revenues. What price should they set? All right, what that means is on your graphing calculator, you would, in Y1, you would graph your quadratic for the revenues, which would be 6 minus 0.1 x times 100,000 plus 5,000 x. And then in Y2, you would graph Y2 equals 700,000. And what we want to do is find at what price would we get the lowest value, what would be the lower price where we could earn 700,000 in revenues. And what happens is when we do this, we find that our x value, we're going to get two different x values when we do this. And if this is y is equal to 700,000, we're going to get two different x values. And the one we're interested in is this one, because that's going to represent a greater decrease in price. Because at this point we have an x value of 34.14, excuse me, 0.14, which means that our new price is going to be 6 minus 34.14 times 0.1, which is going to be equal to 6 minus 3.41, which means, in other words, our new price is going to be $2.59, and that means at that price we'll sell enough dolls that we'll earn $700,000, but we'll have a low price and we'll hopefully drive our competitors out. That's the goal here. Okay, now we go on to our next problem. And we have a quadratic that has roots at 2 minus root 3 and 2 plus root 3. And this, as I corrected in class, should be the point 10, 0. And so what we do is, because we have the roots, we set up the the factored form. So we get y is equal to a, which we don't know, times x minus our first root. So minus this would be minus 2 plus root 3 times x minus 2 minus root 3. Okay, notice these two are both negatives here. It's x minus the first root, x minus the second root. What alternates between positive and negative is this sign right here. Okay, when we multiply this out, we end up with x minus 2 plus root 3, x minus 2 minus root 3. That gives us x squared minus 2x plus root 3x minus 2x again plus 4 minus 2 root 3. minus root 3x plus 2 root 3 and minus 3. Okay, notice these cancel out. So anything that has a root 3 in it cancels out. What we're left with is x squared minus 2x plus 4, or x squared minus 4x plus 4. That is just the perfect square trinomial of x minus 2 times x minus 2. The other piece we have left is this negative 3, which is just root 3 times negative root 3, and so we end up here with x squared minus 4x plus 1, and then all of this multiplied by a. So we can plug in any value of a, and what we'll end up with is a quadratic that will pass through these two roots of minus root 3, 0 and 2 plus root 3, 0. So the things that would change would be that the vertex would change, but the roots would stay the same as we change a.